Okay. Okay, so let's start from there. So we have the three waveforms, and we said that this has. We told that this has a starting point from here, and then you realize the starting point for that would be here, and the alpha angle is given there. Now, if somebody gave you a signal like this and asked you to write a closed form equation, closed form expression for it, immediately, if it was the blue one, you would have no trouble. We'll say, for example, this has a maximum, I guess, magnitude of this value, right? So V of t. Now remember, all of a sudden, all this time since we were talking about the DC voltages, we have V. Now we are not looking at just some value, but an instantaneous value. At that instant, what is the value? Because it can now, because it is alternating for each instant, the amplitude and the angle could be basically different. So if somebody asks you to give a closed form expression for this blue cycle, you would have written Vm sine of omega t, hoping that this angular frequency is going to be omega, right? Angular rotational frequency omega. Now the question is, somebody asked you to write an equation for the red one, what would it be? Yes? Okay, you would have written Vm sine omega t plus theta, right? Because you realize when this value, when you have omega t being equal to minus theta, it will give you the same starting point as the other one. See, if you had this equal to 0 or this whole thing equal to 0, you will be starting point is still the same, 0, right? So you realize that will become 0 when omega t is equal to minus theta. So that's how this equation was actually derived. So if I look at the green one, it will be Vm of sine and omega t and minus alpha. So now we have found the interconnection between a rotating phasor plus the equation that you write down in the time domain, and also how to draw that in the VT axis. So now we did all that. That's fine. So now we have learned everything that is necessary for us to start on the AC analysis. Now the question is, all this time what we were trying to understand, trying to do were things associated with DC voltage sources, voltage and current sources, and primarily only with resistance. There is everything else. Now we are quietly trying to bring in the other two elements, right? Other two elements, which is a capacitor and an inductor. Now the question is, when you bring a circuit into, I guess, AC domain, how does it look like, right? So that's the first thing that we are going to look at. And to look at it, we will try looking at these three elements separately and see. So let's first take the one that we all know, which is actually a resistor, right? Now all these years what we did was, we had a resistor, we call this I, we call this plus minus V, and those were fixed. Any instant you figure out, you look at that thing, you take a snapshot, they are the same. Now all of a sudden I am saying it's not the same, right? It is not the same. Each instant these values are not the same. So we have a resistor. Through the resistor, basically the current flow is now going to be a function of T rather than just being a fixed value. Then I have plus minus. Voltage drop is also a function of T. Any instant, that's the V and the T. And then you have a resistance value of R. Now, whether you have an instantaneous value or anything, the Ohm's law should still work. It tells you at some point in time the interconnection between V and I and R. So, you have an expression that says Vt is equal to IR of T times R. V equals IR. Ohm's law should work with this. Because why? It didn't say it should not be instantaneous. This should work. Now let's assume that IR of T has the general form of Im, which is the maximum I. This looks very much like this. See, Vm, right? That is sinusoidal circle, into sine of omega t. Let's say we assume this. Then immediately from this equation, we understand Vr of t is equal to simple Im times R into sine omega t. Now we have two expressions. We got two expressions. If we got two expressions, I should be able to draw that. No, I don't need this. I should be able to draw this as the time domain expression. So let's start with this. Anybody knows how to draw that? It's a sinusoidal waveform where this peak value is Im starting from here, because there is no angle in here, because we understand this one, which is the blue one, it didn't have an angle and it looks like this, and that's how we draw it. Now the question is, what is that? How do I draw the output voltage waveform? Now you realize this voltage waveform has Im multiplied by R, so which means the amplitude should be higher, but it still looks like a what? Looks like a sinusoidal waveform with no angle shift, no phase shift. So this, if you draw, should look like this. Yes, and this peak value would be Im into R. It's basically an amplified version of the same waveform, and it's drawn like this. Now we have shown you a couple of different ways in which this same information can be shown. A very straightforward way was drawing something called the phasor diagram, right? Something called the phasor diagram. So if I draw that particular phasor diagram, I realize I have to draw like an arrow where the peak value is Im, right? It's horizontal, no phase shift. Right? How do I know here? No phase shift, that's where it should start. And this amplitude should be the maximum value that you're going to get. So there you are, I've used it and drawn it. What would be the phasor diagram for Vr of t? Now Vr of t, we realize, still is going in the same direction, but the amplitude is a little higher. But you realize both of them are on the horizontal axis because there is no angle in this equation. Right? So this is the AC, alternating current representation of a plane wave resistor. We have resistor, we have drawn. Actually that's blue. When you go home you realize the second one and 2 is blue. Right? It's a class A. We have shown what? How to apply the equation. You got an expression for it. There you go. We also showed how to draw the magnitude versus t. So we get an idea of what these waveforms look like. Then we have also drawn what is known as the phasor diagram. I'm hoping R. Oh yeah. Right. Absolutely. Right? What can I say? It's right. It's right. When you're right, you're right. Let's say R was greater than 1. Because if we're less than 1, then the. See, that's the kind of question that you should be asking. Right? Because then you're online paying attention to what goes on. Yeah? Very good. Yeah, good. Of course, now the problem is not there. But phase lag. So out of this, the most important part is what? Phase lag. We did it. Phase lag looks nice. Same way, but they are of different sizes. Now let's take a look at the same analysis that you are doing here for a capacitor. Here you are. Now all this time we did not use this. No circuit had this. Let's look at a capacitor with a capacitance value C, and the current flowing through that is IC of t, which is instantaneous current, plus minus the voltage drop Vc of t. Now tell me the equation that correlates Vc, It and C. Yeah, what is it? The previous group did not know this. Yes, go ahead. Oh, okay. No. There is a sort of differential involved. Differential. You have heard the equation IC is equal to C times dVc over dt? No? Not right? No. Okay. You're hearing it for the first time. You have IC of t is equal to C times dVc over dt. This is the expression that correlates how the current and the voltage is going to change across a capacitor. How many of you heard this before? Some? You not heard it? Is it available or? Right. Can I ask somebody who has done basically learned anything with the rules? No? So another thing that we have to do. Yeah? Because we have to bridge what is going on. So your job is to immediately find out what is missing in all the lectures, right? And then we will fix it, right? So maybe next time I should assume this, everybody knows this, right? But this is a standard equation which you obtain now. I cannot go down to the level of trying to show you how this equation is obtained, right? Because then I have to go down to the equation that you just now wrote, right? And integrate that to show that this is what is going to come out, right? As far as I'm concerned, that's too much to go in deep in this course, right? But we will do that somewhere outside, right? We will have another lecturer doing it outside. But this is the CdVc over dt is the equation that is correlating how the things change across the capacitor. Now, if I assume that Vc of t is equal to Vm times sine omega t, I can assume anything. I assume this. Then immediately, what can you say about this IC of t? It is going to be C times dVc over dt, and this will be Vm and sine of omega t. Now this is equal to what? This is equal to Vm times omega c, right? V and omega c cosine of omega t, right? You probably would have done some sort of differentials in your classes, and then you realize d by dt of sine theta is equal to cosine theta. So I have used that here, right? I have used that here. Now, I am going to rearrange this. So if I take it, IC of t is equal to Vm c omega. Here I am going to put this as sin omega t plus it's 90. Now you need to know these trigonometric identities. If you do not know the trigonometric identities, make sure they end up in your A4 size paper. So now remember, when you bring A4 size paper, don't bring the A4 size paper and then also the brother of the A4 size paper and the sister of it, but a single A4 size paper. You say only has to come. Right? Just one paper. Right? Make sure it's not legal size also. Then it becomes illegal. Right? The legal size paper is legal, it's not A4. Right? A4 is A4, right? So here, now I got two equations. This is slightly different from the resistor, right? Slightly different from the resistor. Now if I write the magnitude versus key for this one, no trouble, right? No trouble, we understand this is a simple sinusoidal waveform where the maximum value is Vm, right? But what about here? What about this? Here you realize there is a amplification of the, of course, omega greater than 0, I don't know whether it's bigger or smaller, but let's say it's bigger, right? You got some amplification of the amplitude, and here this is 90 degrees out of phase. So if I draw it, it will look like this. Right? It will look like this. And this one is going to be Vm times c omega, assuming that is greater than Vm. Right? So now you realize there is a phase shift between the phase shift between I and the V as things travel through a capacitor. Now you have done charging of a capacitor, discharging of a capacitor, yes? Those things you have done. So if you did those, you should have seen this equation. This is the equation that you used when you charge a capacitor and then discharge a capacitor to find the diagram. They give you all those things and then you say, okay, that's it, and then okay, now also I'm doing the same thing. I'm giving it and then you say, oh, that's it, and then you start from there. Right? But we will give you a person to look after the other part of it, how this was obtained, right? Now, the question is, how do I draw the phasor diagram? Now here I can draw the phasor diagram for V. There's no problem. Vm, no angle. That's where the phasor looks like. What about the phasor for this? Phasor for this. Now here the angle is 90 degrees. So you would have a phasor diagram where this I, which is Vm times c omega, is 90 degrees out of phase with the voltage. Now let's look at this. If I keep it like this is Vm, the voltage, and that is the current, and I now move it. If I move it forward, which one leads which one? You realize I leads V all the time. Right? I leads V all the time. Now there's a little sort of an equation which is used to keep who leads who in mind. Otherwise, when you go through all the equations, only you figure out which one is leading which one. So here is an expression which is called civil, which anybody can remember. You realize the top section of it, C, stands for the capacitor. You have I leading V, right? You have I leading V. If I look at the other part of it, look at the other part of it, you realize for an inductor you have V, which will lead I. Right? We are going to see it in a little while. Right? So now you realize if I take a capacitor, if I want to draw the phasor diagram, that's how the phasor diagram is going to look like. This is how the phasor diagram is going to look like. Right? Now, I want to extend this a little bit more. Now, if I look at this expression, right? Look at this. Okay, if I look at this expression here, I have IC of t is equal to Vm times C omega sine of omega t plus you have 90 degrees, right? I have 90 degrees. Now, if I put this particular phasor, in complex form, you realize this part of it would be Vm. If I want to take this particular phasor and I want to represent that in the complex form, that would be what? J times C omega Vm. Because why? That amplitude is in the J omega axis, right? That's why the J part comes in. So J C omega Vm. So essentially this 90 degrees that you have here is the one that is going to incorporate the J into the program, right? So I can rewrite this as V of t times J times C omega. Because why? This 90 degrees is going to generate the J to indicate that it's vertical. And then once I take away this one, 90 degrees, I have what? Vm times sine omega t. And Vm times sine omega t is already known to be Vc of t. So in fact, this is Vc of t. Right? Vc of t. Now, if I look at this equation and say Vc of t is equal to, I have Ic of t times 1 over Jc omega. Now this looks like the Ohm's law. V is equal to IR. Vc is equal to Ic times something that is like an R. But the only problem is this is not a resistance. It is basically what? Dependent on some frequency. If the frequency changes, this is going to change. Whatever frequency change that you have, resistance will change. No, resistance is resistance. Whatever frequency, resistance is still the fixed value. Here, all of a sudden, this looks like a resistance. But if I change the frequency, everything changes. So this kind of thing is called reactance. Right? This kind of thing is called reactance. Now, I am only going to introduce the word, but when you go home, I would have given you some stuff to read which will explain what this reactance is. You are supposed to read it. Called reactance. So now this is like V is equal to I times R. So I can rewrite or maybe redraw that equation, that the stuff that I had earlier, where this is Ic of t, that is Vc of t, right? And this now has some sort of a resistance value, or maybe called a reactance, of 1 over Jc omega. Now this is the starting point of the AC analysis. You have a circuit which has a resistor, which has a capacitor. Now, if I take the capacitor out and I replace it with that is the AC equivalent circuit that we are now analyzing. Right? So that's the first step. Good. Let's leave it like this and go to the next one and come back to this at some point in time. Now, I would also like to show you the same sort of working for an inductor. Right? Now again, if I take an inductor, this is plus minus, this voltage drop is VL of t, this is IL of t, and it has an inductance value of L. Now the equation that correlates the inductance and the and you have IL and VL together is you have VL of t being equal to capital L, right, DIL of t over dt. Again, you may not have seen this. Again, we will try to make sure somebody comes and teaches you how they obtain this, right, from basics and so on. But this is the expression that you would have used to interconnect VL and IL with the inductance value L. This is how things change, right? So this is okay. So now we are going to use the same technique we used earlier, saying IL of t is equal to simple Im sine omega t, right? Then if I put it in here, I would get VL of t is equal to L. Sorry, you got Im L omega times sine omega t plus 90. Right? You do the math in the middle, same sort of math that I used earlier. That's what you're going to get at the end of the day. So now if I draw this, I realize simple sinusoidal waveform for IL. Right? Simple sinusoidal waveform for IL. And here you realize this one value, of course the maximum value of this will be Im. Here you realize that is multiplied by some factor, and we are hoping that this is greater than that, and this is again 90 degrees offset. So I would have my that's what it will look like, right? That would be VL of t, right? And then again, if I draw the phasor diagram, you realize this one does not have an angle, so you have I of m indicating IL. Then this one is how much? 90 degrees out of phase with that, 90 degrees out of phase, and it is Im times L omega. Right? Again, if I want to put this into a complex number form, I would have put it as J times Im times L omega. See, it's a complex number. This would be the same number. So you realize here the V is going to lead I by 90 degrees. Right? So here CIVIL. So if it is an inductor, V leads I by 90 degrees. Right? So this is going to be the phasor diagram of an inductor. Now I want to extend this again, just like in the earlier case. If I take this equation, I have VL of t that is equal to simple Im L omega times sine of omega t plus 90. Now if I consider this 90, I would have to put a J times L omega in here, and then I have Im times the sine omega t, which would have given me simply IL of t, right? VL of t. Now again, let's look at this. This looks like the Ohm's law. This is V, this is going to be I, and that looks like a resistance. This looks like a resistance. But JL omega, you realize it is a complex number, hence we can't call it a resistance, so we call this the reactance. Right? Call it the reactance. So this is the equivalent AC representation of an inductor. Equivalent AC representation of an inductor. So essentially what I am really saying is that if you are doing an AC analysis, that would be IL of t, that would be VL of t, and this would take some reactance value which is J times L omega. Right? Now we have put together almost everything that is necessary for us to do some AC analysis. Right? Now here, let's take a simple example. Here is some sort of a circuit which says Vm sine omega t plus 60 degrees. That's a sinusoidal waveform, right? Vm times the sine of base omega t plus 60. Now you have an inductance. Sorry, you have a resistance, you have a capacitance, you have an inductance, ground, this is R, C and L. Now they ask you to analyze this using AC What is the first step? Take this circuitry, convert it into an AC analyzable form. How do I do that? How do I do that? I have to change this AC into a AC analyzable form. Do we know this? No. We are going to learn. We don't know this yet. Let's leave that. But since we already know RL and C how to convert it, let's do that. There you are. R is always R. No change. Here, this is C. So I have to substitute with 1 over JC of this omega value. JC of omega. Then I have an inductor. I have an inductor. That inductor should be JL omega. There you are. Now it is in AC analyzable form. Because why? I replace all the components with their AC equivalent circuits. JL omega and 1 over C omega. Now let's say take this one had a voltage of Vs. I don't know. Once you convert it to AC, let's say it had a voltage of Vs. Now I want to apply the Kirchhoff law to identify this I, which is actually the current that is going to flow through this circuit. Let's apply the Kirchhoff law. How do I do that? This current is going through the resistor. That way, voltage drop is this way. This one, the voltage drop from negative to positive, that way. Here, it's going this way, the voltage drop should be that way. Going down, the voltage drop should be that way. Now I apply my Kirchhoff law as if I am applying it to any other circuit. How would my equation come out? I have Vs, right? I have the Vs is going this way. So I am applying Kirchhoff voltage law in the clockwise direction. I got Vs. This is minus I times R. I got what? Minus 1 over JC omega times I. See? And minus JL omega times I. There you are, is equal to 0. So if I want to find out I would get Vs over R plus 1 over JC omega plus JL omega. Right? This is equal to what? This is equal to Vs over R plus J, and this is base L omega, right? And minus C omega, because we know that J over, we know that is equal to what? Minus J over C omega. Because why? J times J is minus 1. So if I multiply from here J up, so this becomes minus 1. So it's minus J over C omega. That's how I got this. So this is a what? A complex number. R plus J times something. A plus JB kind of form is what you get. So you see, now the moment you know this part of it, AC analysis is finished. We're done AC analysis. Because what? Everything else, applying the laws, the superposition, mesh, all of those things are still the same. No difference at all. Only thing is you are working right now with complex numbers rather than the fixed values that you are working with earlier. That's it. Right? The only part that we don't know is how do I convert that voltage source into something that is analyzable in the AC form. Right? Now I will talk about that now. The first question that I want to ask prior to this is, do you know what is RMS value? Have you heard of RMS value? Root means square value. So what is exactly the meaning of the RMS value? Yes, what is the RMS value? Is it important for us? It is mathematical, yes, because there is a mathematical equation for it. You realize the RMS, call it I of RMS, which is called the root mean square, root mean square, RMS, is the root of one time cycle base integrated over a single time cycle of I squared t of dt is the RMS value. Right? Now tell me somebody, what is the real, what exactly is the importance of the RMS value? Is there an importance of the RMS value, or is it just somebody came up with the RMS value, so we have to learn? Now just take a look at it. Just take a look at it. Now if you have a sinusoidal signal called I of t, right? I of t. Could you draw me, this is t, could you draw me I squared of t? Tell me, what is I squared of t? Can you quickly draw I squared of t? What does the graph look like? Just quickly say it. There you are. Good. One, there's the other one. I want I squared. Got it? Okay, I got two people. You have not in question. Yes, it's correct. With I squared, what happens is what? Anything negative becomes what? Positive. So, your diagram will look like this. Right? So now you have taken two of them, brought it up, and this integral means what? Yes, when you take a graph and integrate it, what are you going to find? You find the area under the graph, right? If you integrate I squared t, you are going to find the area under the I squared t graph. And once you find the area under the I squared t graph, and since this is t, if I take this area over t, what is this? That's like an average value, right? That's like an average value. So essentially, what you are trying to find out here is that you add up everything, then take an average over t, take the root, what you are going to get is a DC value. It's a constant value. It has nothing to do with the t after that, right? It's a simple value. So this essentially, basically the RMS means that you are trying to take an AC waveform and trying to find the equivalent DC value of that AC waveform. Right? This is like trying to find an equivalent DC part of the AC waveform. Now, as of now, that's enough. But when I come back next time, I'm going to teach you about power. And then you realize the RMS value is the equalizer for signal power. Whether it is AC or RMS DC, the signal power is the same. Right? I will show that when I come back next time. But as of now, you realize that this is sort of converting your AC sort of information into a DC value. That's what is meant by an RMS value. And it so happens that in AC analysis, you need to convert all your sources into RMS values. Right? RMS values. Now the question is, what do I get if I convert it into RMS values? So let's look at that. So if I start off with I of t, which is equal to base Im times sine of omega t, If I substitute that into this equation, I would get I of RMS is equal to root of 1 over T going through a particular time cycle. Then I squared T is I squared times Im, then I squared of omega T and dt. Now can you do this integral? You did in your advanced level, in your advanced level, or O level, I'm sure, O level, you did something called cosine 2 theta is equal to 1, right, minus 2 sine square theta. You didn't do this? Yeah, you did. O level. A level. I wouldn't be surprised if this was taught at O levels also. Yeah? Now, I can substitute from this. So, I have this being equal to IRMS being equal to root of 1 over T going through a time cycle of let's say I put Im squared here, right? Im squared took out. This one is now equal to 1, right, minus cosine 2 theta over 2 dt, right? Now if I take a sinusoidal waveform, a cosinusoidal or sinusoidal, if I add them up all together, this side is plus, that side is minus, what would I get? If I integrate something like sine theta d theta or sine 2 theta d theta or something like that, what would I get? I will get 0, because why? The average value of this is plus minus, when you add up together is 0. Go home and check it. Now this you did in your advanced level. So if that's the case, here I would get IRMS is equal to root of Im squared over T, and from here I would get 0 to T, I would only get half dt. Now half dt is equal to what? Capital T over 2, right? So capital T over 2, I would get root of Im squared over 2, right? If I integrate it, what is this? Im over root 2. So the way you are going to convert a regular AC waveform with a maximum value of Im into RMS is by simply dividing by root 2, right? Root 2. Now let's go back to, so we'll leave it like this, but when I come back next time, I'm going to teach you signal strength, I will teach you energy, power, all of those things. I will show you how the RMS is going to interact with that. Now let's look at this. Still not done. We look at this here. This is Vm sine of omega t plus 60. So we have Vt is equal to Vm sine of omega t plus 60. Now to convert this into an AC analyzable form, we have to convert this into RMS. Now RMS is what? RMS is a peak value over the root 2. So I would get Vm over root 2, and because this has an angle of 60, I would get a 60 degree angle. And I substitute, right, that in my circuit. Right? In my circuit. So if somebody comes and tells you there is 200 with an angle of 40 in your let's say somebody gives you a circuit with 200 times 40 and asks you to draw the sinusoidal waveform, you would do what? You would say, oh, okay, if this is the case, this is going to be equal to what? 200 times root 2 sine of omega t plus 40. See? That's how you would look at it. If somebody gave you this, if somebody gave you this, that would have been the original waveform. If you know the original waveform, I can move it into RMS in that manner. So now we have understood exactly how this has to be done, now I will show you a simple example and simply explain to you that AC theory I can just stop right now. You will be competent in AC theory. Right? But we are not going to do that. But if I did, you will still be able to solve problems. So let me take a problem from the textbook. You don't have anything else after this, right? Yes, what do you have? Huh? I told him I'm taking another 15 minutes out of his mechanics students. Right? Good. Here. There is a circuit with an AC waveform. Here you are. This is plus minus E. That is I. This is R. This is C. And they have given. Now here remember. Still not over. Don't pack your bags. Now when you analyze these circuits, you need to give the frequency. Not like the DC. DC did not have a frequency. Now here you have to give the 60 Hertz. If they do not give the frequency, what are you going to base assume? What is the frequency of the AC waveform? 60. It's 50. Right? Would you forget that? It's only 50. Right? But since we are using all these books, American books, they have 60. If you got 60 as the frequency, you have low, voltage. If you simply have high voltage, the frequency becomes low. Right? Because we are low. So, anyway, if most likely I will state the frequency. If not, if I didn't state the frequency, if you do need the frequency, take it as 50 Hertz in your system. Right? So here, okay, so they give the frequency and E is given as 120 volts with an angle of 20. Now here this is in RMS form, because why? In AC waveforms, if you take a look at AC circuits, they give it to you in RMS form. Then R is 18 ohms, C is 91 microfarads. Let's try to analyze this problem and find I that flows through the circuit. Okay, here's what I'm going to do. I have to find the AC equivalent circuit. How do I do that? I have to place my C with JC omega. Yeah? So now this is equal to what? JC is 91 times 10 to the minus 6, which is micro, and the frequency is 60 Hertz, but this is omega, so it has to be 2 pi times 60, right? And that works out to be, right, minus J29, right? That works out to be, right, minus J29. Then I have to basically replace all of these things with their AC equivalent. So AC equivalent for this is what? 120 volts with an angle of 20 degrees. That is I. This is R is R. So it can be 18 ohms. Sorry, we just write 18. That's the AC equivalent of the resistor. And here I write minus J29 and I have my circuit. Now I apply the Kirchhoff voltage law. I would get what? 120 at an angle of 20. See, if I apply the Kirchhoff voltage law, this drop is going this way, this drop is going this way, this drop is going up. You have minus, you got 18 times I, right? You got minus J29 into I is equal to 0. So I will have I being equal to 120 with an angle of 20 degrees over that plus J29. 29. Now you realize this is a what? Basically a division. Hence this you need to convert to r theta format. If you convert this to r theta format, immediately you can find the answer. And that's in amperes. Right? It's that simple. There you are. If I can put these values, it's simpler. Now I want to go back a little bit to the question earlier. Right? There was a question JL omega, right, plus 1 over JC omega. Right? Now if I take this, I have 1 over JC omega. Right? I want to make sure that the J part goes up. So how do I do? I will multiply this by J on the top and the bottom. So you got J on top and J squared and then C omega. And we also know that J is equal to root of minus 1. Yes? In the complex number, J is equal to, or I guess in your case it was I that was equal to, I guess, root of minus 1. So you got J squared to be equal to minus 1. So if I substitute here minus 1, that works out to be J over C omega. And I substitute here, I would get R plus J times L omega, right, and minus J over C omega. And that is equal to 1 over R plus J and L omega 1 over C omega minus 1. This is how I got the earlier equation. Right? Earlier equation. So now we have understood the most fundamentals of AC analysis. Now, only thing you have to do is to apply some very complicated AC circuits can be taken. And you can apply the Kirchhoff rules, the mesh analysis, nodal, superposition, Norton, Thevenin, you name it. All of those can be applied to this, and you consider these to be the sources, just like DC sources. Only thing is that you have to now do all the calculations in terms of complex numbers. Right? Now I will stop this right now, and I will ask you a question which you are going to answer to me next time. Right? So maybe I will do that. Right? So if I ask you a big problem, and then also, ladies and gentlemen, over the past week, I got a lot of emails and things on like WhatsApp and all kinds of stuff. I'm very happy because I know that there are a lot of you who are now engaging with the course material and trying to do the problems. They get stuck and they send it to me. I try as much as possible. In any place I take a piece of paper, I can remember there was a question that was asked by a student, and I took a piece of paper on the other side and I wrote the question, took the picture, read it. I was on the road and I sent it. Right? So you keep doing that, because ultimately what's going to happen is you are the one going to actually, right? I just try to get something out of it. But please don't think that you are going to get a repeat examination even if you stand on your head for the year 1 like last time. Right? And then I'm telling you, if you by any chance fail more than 4 subjects in the first year, right? In the first year, you fail more than 4 subjects, then if you go to the next year, you will keep adding more subjects to that. Right? They will keep adding more subjects to that. So if you fail more than 4, stay back. Right? Do the course, then go to the next level. Because I will tell you, calculate it and see. You will be spending more money by trying to go forward with many repeats. Right? You are spending more money because you keep on failing. And the rules now are getting a little strict. So better throw away everything else outside. Start concentrating on this course and doing the questions and then try to pass the exam in one shot. Right? Good. Sorry.